Section 3.5 is quite the lengthy section. This is probably a lengthy video, uh, which is why I don't recommend you watch this whole thing in one sitting. We can actually divide this section in 3 parts, and I'll make sure to point those out when we end a part and when we begin a new part. Because, like I said, all 3 together make this long video, which you probably don't want to sit through. So we'll start with duality. First things first is we're going to define what a linear functional is. Now you should be familiar with linear functionals. Maybe you've never really heard of it being defined like this, but a linear functional on V is a linear map from V to F. In other words, a linear functional is an element of a vector space of the linear maps from V to F. And remember, F here is just a number, right? It can be a complex or real number. So what it's doing, it's just spitting out a value, right? This linear map is getting an element from V and spitting out a value, a number. So an example, and from R3 to R, this is a linear functional. Now how is it defined? It's defined like this, x, y, z, whatever numbers you plug in there, x, y, z from R3, right? That's an element of R3. You just plug those numbers into x, y, and z, and it should give you a real number, right? So if x is 2, y 2, z 2, it'll be 4 times 2, which is 8, minus 10 plus 4, which is 2. So that's how we get that. It spit out a value, right? The range are the numbers. In this case, the real numbers. Another example of a linear functional is if we map from Fn to F, that is another example of a linear functional. And we can just define it like this, some linear combination where C1 to Cn are all elements of F. So this linear map is also a linear functional. Another example of a linear functional maps the polynomials, all polynomials, the vector space of polynomials to the real numbers. And the way we do this is integrate from 0 to 1. Right, so we know polynomials are continuous, so we know they are Riemann integrable. So we can take the integral from 0 to 1, and that'll spit out a value. So here, phi, this linear map phi, is also a linear functional. So that's what linear functionals are. Taking elements and spitting out a value, where the image is the real numbers, maybe the complex numbers, but we get an element of f. Also, the dual space of V. So if we have a vector space V, the dual space of V, denoted V prime or V apostrophe, is a vector space of all linear functionals on V. In other words, V prime is equal to, again, the set of the linear maps from V to F. Here is a theorem. Suppose V is finite dimensional, then V prime is also finite dimensional, and it turns out that the dimension of V is equal to the dimension of V prime. Now, this proof follows immediately from a theorem we've seen before. Okay, so I don't mention it, but I should just write it here. Remember that the dimension of F, I should write dimension of F is 1, right? So the dimension of V, we'll just say it's n. So the dimension of V prime is equal to the dimension of V times the dimension of F. Oh. Which is just equal to the dimension of V. That's how we're getting that, which is n. Right, so here the dual space V prime is, again, the set of all linear maps from V to F. And here, V is just a vector space V. But those two have the same dimension because of the theorem that told us, I actually didn't state the theorem right, but let me state that theorem. Dimension I keep messing this up. The dimension of L V to W is equal to the dimension of V times the dimension of W. Remember that theorem? So that's where we're getting that from. We're multiplying dimension of V times dimension of F, which gives us dimension of V. Okay, next definition is if V1 to Vn is a basis of V, then the dual basis of V1 to Vn is a list phi1 to phi(n) of elements of V prime, where each phi j is a linear functional on V, such that, so here, if we get one of these elements of the basis of V, and it matches with our phi j, the k and j are equal, then we assign it a 1. Otherwise, we assign it a 0. And that gives us a dual basis. That's how we're defining this dual basis. Okay, example, what is the dual basis of the standard basis? So, basis, if we have Fn, well, what's the standard basis for that? We have a standard basis E1 to En. So for 1 to n, we define phi of j, again as we did in our definition, to be the linear functional on Fn that selects the jth coordinate of a vector in Fn. And we just apply a definition. So in other words, phi of j, we take this vector of Fn, which is just equal to x times j, right? Because all the other, for all the other vectors or components actually in the vector, we have a 0 coefficient, right? Because k and j don't match up. It only matches up for the jth component. So that's why we only get the x sub j. So if you see this phi sub j, the dual map just spits out the x sub j. So it's a simple way of defining what a dual basis is. So phi1 to phi(n) is a dual basis of the standard basis, and yeah, that's all it is. Again, as long as this j and this k match up. So for example, phi of 1, that's not a phi. I'll draw it over here. Phi of 1, sorry, 1 of x1 to dot 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 x will spit out x sub 1, and so on and so forth. So it's quite a simple way to define a basis, a dual basis. Okay, so this theorem follows. Suppose V is finite dimensional. Then the dual basis of V is a basis of V prime, of the dual space, right? So, not much to it. Suppose V1 to Vn is a basis of V. Let phi1 to phi(n) denote the dual basis. Well, to show that phi1 to phi(n) is a linearly independent list of elements of the dual space of V prime, we suppose that a1 to an are coefficients of the phi vectors such that we can get a linear combination equal to 0. Now, what do we need to show for it to be linearly independent? Well, we need to show that a1 to an is have to be 0 for that whole linear combination to be equal to 0. So if we apply this linear combination to Vj, we get a sub j for all j, 1 through n. Well, then the equation above simply means that in order for us to get 0, a1 to an are going to have to equal 0. Right? In this case, we're getting aj. So when is that 0? Well, when aj is 0. And what is aj? Well, it could be a sub 1, a sub 2, a sub 3, a sub n. Right? So they all have to be 0 for us to get the linear combination is equal to 0, therefore showing that phi1 to phi n is linearly independent. Now, because every linearly independent list of vectors in V with length dimension of V is a basis of V, and the dimensions of are equal of the vector space and the dual space, well, then we get that this is a basis of V, of the dual space of V or V prime. Right, so we show that this, the dual space is linearly, the dual basis is linearly independent, and the dual space has the same dimension as the vector space V. Therefore, phi1 to phi n is a basis of the dual space. So this may be a bit tricky, mostly definition of dual basis, but it's really, how can I say it? It's quite simple. You shouldn't overanalyze this. This slide is pretty straightforward. Nothing much to go into. So we'll move on again because this section is a lengthy one. Okay, so I do have an example here. But before I do go over that example, we should define what a dual map is. This is maybe the definition we'll use the most, even though all the definitions from the previous slide are important. As you can probably imagine, anything with the word dual in the section and the lecture of duality is important. So here, a dual map is the following. If T is a linear map from V to W, then the dual map of T is a linear map T prime that maps from W prime to V prime, or the dual space of W to the dual space of V. And we define it like this. So T prime of phi is a composition of functions phi of T, which is just another way of writing phi of T of V, where again, V is an element of the vector space V, and for phi being in the dual space of W. So really, whenever you see this, just remember this over here. That might be easier for you to remember. Now, is the dual map actually a linear map? Well, if T maps from V to W, or it's a linear map from V to W, and phi is in W prime, then the dual map is defined to be the composition of the linear maps phi and T. So we know, as we have shown before, that the dual map is indeed a linear map from V to F. In other words, T prime of phi is in V prime. And then the verification that T prime is a linear map from the dual space of W to the dual space of V is straightforward. But before I even do go on, let me just kind of draw a picture for what we just did. So for this right here, I'm going to draw a picture. It says from V to F. Right, so T maps from V to W phi maps from W, sorry, not from W, from V to F. So if we do phi of T of V, we get that we're mapping V to W. And then here, phi I'm going to call W because it's now our new domain. We get this element and map it to F. And that is what the dual map does. That is a composition of functions. So that's what that's saying. So that's why over here we get that the dual map is indeed an element of the dual map of V, because again we're mapping from V to F. So it's a linear functional. Okay, so we're going to verify now that the dual map is indeed a vector, sorry, not a vector space, a linear map. So here we have two linear maps, elements of the dual space of W. Well, then if we apply the dual map, we get that this is the definition, right? Which is equal to this here, and it just gives us the whole additivity property. Right, so the next step, if lambda is in F, and phi is in the dual space of W, then again, we just apply the definition. We can take out that lambda, and we get that same result, just with the lambda factored out, showing us the homogeneity. We're going to go over an example of what a dual map is, or I suppose a dual map. We're going to go over an example. That'll make things a little more clear because I know that definition can be a bit confusing. So we're going to find D to map polynomial, a polynomial with real coefficients, to a polynomial again of real coefficients by taking the derivative of P, which it shows here. So again, we take P from here and it spits out P prime, its derivative. That's why that's a D, because for differentiation. So suppose phi is a linear functional on the polynomials of R. So again, if it's a linear functional, that means it's going to spit out a number, right? The function should give us a number. On the polynomials defined by, we take the polynomial and we plug in 3 to its variable. That's what this linear functional is doing. Then the prime of phi is a linear functional on the polynomial on the vector space of polynomials given by. Actually, here before I even move on, I should note here this apostrophe here is for derivative, and this apostrophe over here is for the dual map. Don't confuse those. We're not saying derivative of D of phi. That's not what we're doing. We're just saying the dual map of phi is a linear functional on the set of on the vector space of polynomials defined like this. So here we just have the definition of a dual map, as you can see from above. And again, a way to rewrite this. So if you look up here in the definition, we're just doing these three equalities, or two equalities, I should say, three expressions. That's just equal to this composition of functions, so it can help us see things easier, which is just equal to phi of dp. And what do we do here? Well, we have it from over here, right? This is what it's telling us. Take the derivative. So we take the derivative, it gives us p prime. And now the linear functional tells us what? That's from over here to plug in 3 into that new polynomial. So we plug in 3. So what did we do? This dual map simply took the derivative of the polynomial and then just plugged in 3. So in other words, the dual map of D of phi is a linear functional on the vector space of polynomials that takes p to the derivative of p with 3 plugged in. So that's what that's saying. This dual map is just saying take the derivative, plug in 3. Another example, suppose phi is a linear functional on this vector space of polynomials defined by, again, the integral of p. Now instead of derivatives, we're taking the integral of p from 0 to 1. Well, then again, we can apply the linear functional, the dual map definition. We just rewrite this like this, and then we rewrite it like this. Derivative of p is just phi of p prime now. And now if we integrate p prime, what do we get? Well, by the fundamental theorem of calculus, that's equal to p of 1 minus p of 0, which should give us a numeric value, or an element of f. So again, the dual map is also a linear functional, right? This over here is telling us the dual map is a linear functional. We're spitting out a value. And again, these were examples of linear functionals. So in other words, the dual map d prime of phi is a linear functional from the polynomials that takes p to p of 1 minus p of 0. And this to here, this is kind of used in calculus when they're showing that what a derivative and then an antiderivative are. It kind of like reverses the operation, to speak loosely. So that's why p, you just pretty much plug in p1 and then p0, because we're using the fundamental theorem of calculus. Okay, here is a theorem of basic properties. Actually gonna only prove one of them. And I'll probably, let's prove probably the most difficult one. This one, straightforward. Just, again, like I said, simply use the definition of a dual map, and you'll see just how easy that is. Same thing with the second one. The third one changes order. So like the product of linear maps, the dual of the product of linear maps switches the order. And we're going to go over that proof. So suppose phi is in W prime, or the dual space of W. Then ST prime, or the dual space of the product of the linear maps S and T. Again, we're just going to rewrite it as a definition of a dual map. Rewriting it again. Rewriting it again. Rewriting it again. Finally giving us the reverse order we're looking for. Dual space of T times dual space of S of phi. So just look at that equality. All we're doing is using the definition of dual map and showing indeed that this little bullet point of the theorem holds. For the other two bullet points, again, it should also look as nothing but equality. So this is equal to this, and then you end up proving it. So fairly straightforward. Some books or other mathematicians, instead of v prime for dual space, they might use v and then like a little star. And looking at this example up here might have been smart because we use apostrophe for both the prime for derivatives and for the dual map. So that that may have been a smarter choice. So this concludes the first section of the three I was talking about. For the lecture of duality, we're going to be moving on to the second section now. And I don't know which section is the lengthiest one. For sure not the third one, so it might probably be the second one coming up. So again, I recommend maybe you stop watching this video now, make sure that you digest these ideas, you're comfortable with the definitions, with the theorems, because we're going to be moving on to still duality, but something a bit more, or I guess a new section within the lecture. Okay, if this loads, now we will be looking at something called the annihilator. So that's a fancy word. So for U, subset of V, the annihilator of U, denoted U to the 0, is defined by the linear functional phi such that phi of U maps to 0, where U is an element of U. So the way some students see this is just saying the annihilator, pretty much thinking of dual spaces, is kind of like the null space, right? Vectors, it takes a vector and it maps it to 0. And it takes a, and that's when we're dealing with linear functionals. So they kind of, we relate this to the null space, but now it's the annihilator because we are dealing with linear functionals. So what can we say about annihilators? Well, we can go over examples. And actually we should take our time with this example because it's gonna illustrate something that we're gonna be dealing with. Well, kind of like foreshadow into our theorems coming up. So here's the example, not the solution. So bear with me, I know it looks lengthy. Suppose U is a subspace of the vector space of polynomials with real coefficients, consisting of all polynomials multiples of x squared. If phi is the linear functional on the vector space of polynomials defined by phi of p, so this linear functional phi of p is taking the derivative then plugging in 0, well then phi is in the annihilator, is an element of the annihilator of U. So how do we show this? Well, first of all, let E1 to E5 denote the standard basis of R5. So you already know what those vectors are. So for example, E1 is 1, 0, 0, 0, 0. E2 is 0, 1, 0, 0, 0. So on and so forth. So E1 to E5 is just the standard basis of R5. Phi1 to Phi5 denotes the dual basis of the dual space of R5. And suppose U is the span of the two vectors E1 to E2, E1 and E2. So that just looks something like this, right? That'll create a plane in R5, a two-dimensional plane in R5. We're going to show that the annihilator of U is equal to the span of Phi1 to Phi5. Sorry, not Phi1, Phi3 to Phi5. How do we do that? Well, we're going to have to show that U, the annihilator of U, is a subset of the span, right, of Phi1, sorry, Phi3, Phi4, Phi5, and then we're going to have to show that the span is a subset of the annihilator of U. So that's how we're going to show that those two are equal. So something I should mention, I know I've been talking kind of fast, saying a bunch of things, but I should have drew a purple line here. These are two different examples that may have been causing confusion. So again, the first example I kind of like rushed through it. But if we take a look at it, suppose U is a subspace of the vector space of all polynomials with real coefficients, consisting of all polynomial multiples of x squared. Then if phi is a linear functional on that vector space of the polynomials, defined by you take a polynomial and plug in 0 to its derivative, then we simply get that phi is an annihilator, or an element of the annihilator of U actually. And why is that? Well, a multiple of x squared. So 3x squared is a multiple, right? Well, when we take the derivative, what does that do? That just simply gives us 6x. And then we plug in 0 to x, so we get 6 times 0, which is just 0. So this will always give us 0. It'll always spit out 0 because x squared, the derivative is just going to be x, or sorry, the degree of x will be 1 less, meaning it's just x. We plug in 0 and then just multiply by whatever new coefficient we have, in this case 6, and it'll just spit out 0 again. That's why phi there is a linear functional. But now, again, looking at this next example is the interesting one, I should say, where we have E1 to E5 denoting the standard basis of R5, and phi1 to phi5 being the dual basis of the dual space. And we're defining U to be the span of E1 to E2, meaning the two-dimensional plane in R5. Well, then we're going to show that the annihilator of U is equal to the span of phi3 to phi5, those three other vectors in the dual basis. So how are we going to do that? Well, recall that phi j is just a linear functional on R5 that selects the jth coordinate. So remember, whatever this j is, so if it's 2, we'll get that we get x2. That's how phi j is defined. So first suppose that phi is in phi3 to phi5, right? So it's a linear combination of that. Well, then there exists the coefficients c3 to c5, such that phi is indeed a linear combination of those three vectors. Well, if x1, x2, 0, 0, 0 is in U, what does that mean? Well, then phi of 1 of x1, x2, 0, 0, 0 is simply equal to this here. Again, wait, okay, so there's a mistake right there. This one here, that one there shouldn't be there. Let me actually erase that. That might cause confusion. So phi of x1 to x5, phi of x1, x2, 0, 0, 0 is simply equal, well, this is just phi, right? As we had set up here. And then x1, x2, 0, 0, 0. What do we get for those? Well, we just get 0. So what does that show? That shows that phi is in the annihilator of U. In other words, that span of phi3 to phi5 is a subset of the annihilator of U. Okay, now what do we need to show? We need to show the other direction, right? That the annihilator of U is in that span of phi1, phi3 to phi5. And again, just before I move on, phi3 here, what's it going to pick up? This element, phi4, this component right here, and phi5, this component right here. So that's what we get, all nothing but zeros, in case that wasn't clear. So now let's show the other inclusion. To show the inclusion of our other direction, suppose phi is in the annihilator of U. Well, because the dual basis is a basis of R5 of the dual space of R5, there exists C1 to C5 such that phi is equal to a linear combination of that basis. Well, because E1 is in U and phi is in the annihilator of U, we have that 0 is equal to 1. Well, phi of E1, which is simply, again, this is phi right here, as we stated on the line above over here, and then of E1. Right, so here, phi1 corresponds to E1, so this becomes a 1 times C1, which is equal to C1, and all the rest disagree, right? 2 is not equal to 1, 3 is not equal to 1, 4 isn't equal to 1, 5 isn't equal to 1. So these become 0, 0, 0, 0. So that's why we just get C1. So again, because E1 is in U and phi is in the annihilator of U, we get that phi of E1 is equal to C1. Similarly, the same thing we can do for E2. We get that C2 is equal to 0 as well. Therefore, phi is equal to a linear combination of C3 times phi3 plus C4 times phi4 plus C5 times phi5. Therefore, showing that phi is in the span of phi3 to phi5, thus showing that the annihilator of U is a subset of the span of those three vectors of the dual basis. So again, we showed inclusion to both sides. Therefore, we have our conclusion that the annihilator of U is in the span, or is equal to the span of those three vectors of the dual basis. So the reason this example took a lot of space, well, other than the fact that it was long, is because it's, again, like I said, foreshadowing to a theorem that's about to come up. But we will go over one theorem first, and then bring that other theorem up. So suppose U is a subset of V, then the annihilator of U is actually a subspace of the dual space of V. And you should remember what the conditions to check that something is indeed a subspace, what those conditions are. So there are three conditions. One was that we have the 0 vector in there, and then closed under addition and closed under scalar multiplication. So we can prove this pretty easily, straightforward. 0 is in the annihilator of U, right? Because, well, 0 is a 0 functional. The 0 functional applied to every vector in U is simply 0. That just comes from definition of annihilator. Sorry, not even the annihilator. We just plug in 0 to a linear functional, to the 0 functional, and we get 0. So 0 is definitely in there. But now Suppose phi and chi, wait, sorry, that's not chi. Phi and psi are in the annihilator of U. Well, then those linear functionals are equal to 0 for every U and U. Again, because that comes from the definition of annihilator. Right, if they're an annihilator, then give me any vector, I'll spit out 0. So that's what those are doing. Well then, if we just add them, we get nothing but equalities. 0 equals 0 plus 0, therefore it's equal to 0. Therefore, their sum is closed under addition, so the sum is in the annihilator of U. Similarly, with scalar multiplication, we can do the same thing, right? You multiply any vector in U times lambda, but by definition of linear functional, man, I always have trouble with those variables. By definition, that's just going to map it to 0. Same thing if we had the phi of U. It's going to be 0 times lambda, which is 0. So again, same thing with scalar multiplication, and we thus show that what? The three properties. So therefore, the annihilator of U is a subspace of the dual space of V. Okay, next. So now we can move on to the theorem I was mentioning. I didn't mention too much of it, but it has to do with the example we saw on the last slide. As you can see here, there's a little blue box, light blue box. I keep forgetting to hide those. I forgot it last slide and now this slide. But let's continue, as again, this lecture is quite lengthy. Suppose V is finite dimensional and U is a subspace of V. Then the dimension of U plus the dimension of the annihilator of U is equal to the dimension of V. So remember from the last example, we had V be R5, and the dimension of U, well here the dimension of V we know is 5. The dimension of U, we took two vectors, right? So it was dimension 2, and then that dimension of the annihilator was dimension 3, because we had the, remember in the span, we had this span equal the dimension of the annihilator of U. So that's why it's dimension 3. So that's where we get this theorem from. And that's always the case, right? Not just in that example, but always. So that's what we're going to prove. So there's our little proof box. First, let I be a linear map from U to V, and let it be the inclusion map defined by I of U is equal to U for U and U. So if you're not familiar with inclusion maps, that just takes a vector and spits out the same thing. So I of U is equal to U. Well, then the dual map I prime is a linear map from V prime to U prime. And now we can apply something that we've been applying a bunch. The fundamental theorem of linear maps tells us that the dimension of the range of I prime plus the dimension of the null space of I prime is equal to the dimension of the dual space of V. Now here we can note that the null space of I prime is, well, the annihilator of U. right? And we had seen in a previous theorem, one of the first theorems, that the dimension of the dual space is the same as the dimension of the vector space. So we can rewrite the equation as follows. The dimension of the range of I prime plus the dimension of the annihilator of U is equal to the dimension of V. Now, if phi is in U prime, right, so it's a linear functional, it can be extended to a linear functional psi on V such that I, the dual map, I prime of psi is equal to phi. Therefore, phi is in the range of I prime, which implies what? Well, that the range of I prime is U prime. So the dimension of the range of I prime plus the dimension of U prime is equal to the dimension of U. And therefore, all the equation above becomes our desired result. I should mention, I mean, this proof shouldn't be, this is pretty straightforward. Again, get comfortable with dual spaces, dual maps, dual bases, to keep understanding this section. Because next we have a theorem that mentions two things. So suppose V and W are finite dimensional, and T is a linear map from V to W. Well, then the null space of T prime, again, T prime is the linear map, the dual map, I should say. The null space of that dual map is equal to the annihilator of the range of T. Second theorem says that the dimension of the null space of the dual map is equal to, well, you know what, I won't even say the words because it's just too much to get confused. But we get that equation, and that equation really isn't hard to see. We use just a bunch of equalities to kind of see what's going on. So for the first one, it's going to be inclusion showing both sides, inclusion subset, subset to show that that holds true. So let's go ahead and prove A. First, suppose phi is in the null space of the dual map of T. Sorry, the dual, yes, dual map. Well then, by definition of dual map, well, 0, right, from the null space is equal to the definition, or we're just using the definition of dual map here, which is equal to phi of T of V for every V in the vector space V. Therefore, phi is in the annihilator of range of T. Therefore, the null space of the dual map T prime is indeed in the range, or the annihilator of the range of T. Now to show the other side, suppose that phi is in the annihilator of range of T. Well, then phi of TV is equal to 0 for every vector V in vector space V. Therefore, again, applying the definition, 0 is just equal to T prime of phi, which just means what? Well, that phi is in the null space of the dual map T prime, which shows that the annihilator of range of T is indeed a subset of the null space of the dual map of T. So that proves the first one. The second theorem, or part B, the dimension of the null of T prime is equal to the dimension of the annihilator of range of t. Now, why is that? Well, look at the theorem above, right? Or part A. We're showing that these two things are equal. So their dimension should be equal. Now, what's next? Well, from the theorem we saw, actually from the theorem above, what do we see? Well, remember the dimension of the annihilator is equal to, so if you look all the way above, we can just move this over here to give us, okay, look back down to show us that the dimension of W, so the annihilator is equal to the dimension of W minus the dimension of the range. So that's where this equality is coming from. And then from the fundamental theorem of linear maps, we get that the dimension of the range of T is, so this here, remember, is just equal to dimension of V minus dimension of the null space. Again, by doing some little algebra on the fundamental theorem of linear maps and applying that theorem. Which is now just equal to the dimension of the null T plus dimension of W minus dimension of V is now equal to dimension of the null space of T prime. So that's what our theorem was saying. So again, maybe it helps to take the time to draw pictures with this. Just make sure you understand what's going on. Shouldn't be too complicated if you're comfortable with the definitions, otherwise keep reviewing that. So the last theorem, suppose V and W are finite dimensional, and T is a linear map from V to W, then T is surjective if and only if the dual map is injective. That's quite interesting, right? So the linear map, T from V to W is surjective if and only if this whole codomain is taken up, right? So range of T is equal to W. Well, when does that happen? That only happens when the annihilator of T is equal to 0. Right? And what can we rewrite this range of the annihilator of range of T? Well, if you look at the previous theorem, part A, that's just saying that only happens if and only if the null space of T prime is equal to 0. Again, because this and this are equal. And now it's showing that the null space is equal to 0, which shows what? Injectivity, right? Happens if and only if T prime is injective. So that proves that. This annihilator section keeps going on. We're almost done with it. Just one more slide, and we'll be done with this section. So here we have a similar theorem from last slide, but just kind of changing things up a bit. So let's take a look at the proof. The proof for the first one, a bunch of equalities, nothing too complicated. Dimension of range of T prime, or the dual map, is equal to dimension of W prime minus dimension of the null space of T prime. That just comes from the fundamental theorem of linear maps. Right, so that's equal to the dimension of W minus dimension of the annihilator of the range of T, which comes from the previous theorem, right? We showed this null space of T prime is equal to the annihilator of the range of T, which is just equal to the range of T. Right, and that comes from the theorem from the last slide, where we have that the dimension of W is the sum of this and this. So we just did a little algebra, switched it around, and this whole line is equal to the dimension of the range of T, So we get our desired equality, and we're done with that proof. Now B, a little more involved, nothing too complicated again. So we're going to show that the range of T prime is equal to the annihilator of the null space of T. So first suppose that V is in the range of the dual map. Well then, there exists psi and W prime such that phi is equal to the dual map of psi. So if V is in the null of T, well then what does that mean? Well then phi of V, we're just applying the definition that or this little quality up here, is equal to T prime of psi with V, which is just equal to this composition, which is equal to this over here, and TV here, V is in the null space of T, right? Meaning that this is equal to what? To 0. So C of 0, we get 0. Therefore, phi is in the annihilator of the null space of T. This implies that the range of T prime is a subset of the annihilator of null T. Now, what are we going to do next? Show this inclusion? Well, yes, to show that the two sets are equal, but we're going to do something different instead. We're going to complete the proof by showing that the range of T prime and the annihilator of the null space of T have the same dimension. Right? That should complete the proof. So to do this, note that the range of T prime, as the part A of the theorem says, is equal to the dimension of the range of T. That from the fundamental theorem of linear maps, we just get that that's equal to the dimension of V minus dimension of the null space of T. And we know from the previous theorem, where it says this is equal to the sum of the null T plus the annihilator of T. That's where we get this next equality from. And therefore we have shown that the dimension of range of T prime is equal to the dimension of the annihilator of the null space of T. And this concludes our proof. So not too bad. And again, similar to the other one, suppose V and W are finite dimensional and T is a linear map from V to W. Well, then T is injective if and only if its dual map is surjective. So in the last slide, we have the theorem where it was surjective if and only if the dual map was injective. This is the other case. T is injective if and only if T is surjective. And again, this is an if and only if proof where we just use a lot of if and only ifs. So the linear map T from V to W is injective if and only if the null space of T is the zero vector, right? Well, when does that happen? This happens if and only if the annihilator of T is a dual space V prime. Well, that only happens if the range of T prime is equal to V prime. And that only happens if T prime is surjective. Which voila proves our theorem. So this is the conclusion of the second part of the lecture. At 1 hour, we're at 1 hour and we still have a third of the lecture to go. So this is where I would recommend maybe again pausing, stopping here, and maybe seeing the rest of the lecture at another time, just so to make sure you digest the concepts and to not tire yourself too much. So now we're going to be talking about, I didn't take care of that there. Oh my gosh, I keep doing this. Please forget or kind of ignore that for now. We're going to be going over the transpose of a matrix A. I'm not going to read that whole thing because it's long. But if you remember transpose of a matrix, what was that? You just get a matrix and the first row becomes a first column, second row becomes second column, third row becomes third column, so on and so forth. Or the first column of the transpose becomes the first row of the original, so on and so forth. So that's what a transpose is. You kind of flip it on its side. And you may be familiar with this if you're already taking matrix algebra or a course similar to it, or an introductory linear algebra course. And we have the certain properties for transpose. Oh, here's another picture showing that. So here, this is, if we call this A, then this is A transpose. We have the property that if A is an m by n matrix and C is an n by p matrix, then the transpose of the products is equal to C transpose times A transpose. So notice the little change of ordering there. And these proofs are fairly straightforward. If you're not comfortable with matrix notations, they might be a bit confusing. But suppose K is from 1 to P, and J is from 1 to M. Well, then the transpose of the product, we simply write like this. That's just by definition of transpose. And the way we write the product of two matrices, just like that, that's sum. So where does this equality come from now? Well, again, just applying the definition of transpose, we can flip the order. But now, instead of RK, it's going to be KR, right? Rows becomes columns, and column becomes row now. Same thing with the A transpose, which is just equal to C transpose times A transpose, and we get our desired equality. Now, if you remember from the matrix lecture, we could write linear maps as matrices, and this theorem tells us that if T is a linear map from V to W, then the matrix of the dual map is equal to the transpose of the matrix of the linear map T. So this is quite an interesting theorem, but again, it just requires to understand what we're doing and just carry out some equalities. So quite a lengthy proof. Let A be the matrix of the linear map T, and C be the matrix of the dual map of T. And here we're using, so for the linear map T, we're just using bases. If you remember, V1 to Vn, W1 to Wm. And then for the dual bases, Phi1 to Phi and Psi1 to Psi-m. So suppose J is from 1 to M, suppose K is from 1 to N. Well then, from the definition of the matrix of T prime, we have what? Well, we're just going to simply write that as the dual map, T prime of Cj is equal to the sum of the matrix times our bases vectors, psi r, sorry, phi r. And this is just really applying the matrix definition we had from the matrix section to the dual map. And so as the dual map is defined, that's just equal to this here, that composition. So now we plug in our vector vk and vk over here. And what does that give us? Well, as you can see, this gives us the matrix CKJ. Why does it give us that matrix? Well, remember how we defined phi, right? It has to agree with R here. So we get the matrix C of Kj. We also have that phi of j, phi sub j of t of Vk is just equal to this here, which is equal to our, again, we're just rewriting this, remember the linear transformations, or sorry, not the linear transformation, the linear maps as matrices, which is this here. Which, as we had seen previously, again in the matrix section, we could just put this here because these here are just scalars, which is just equal to the matrix AJK. Now comparing the two sets of equations, what does that give us? That gives us that C Kj is equal to A sub Jk. So we just flip those around, right? So C is equal to the transpose of A. In other words, what is that saying? That the matrix of the dual map of T is equal to the transpose of the matrix of T. That's all that's doing. So that is quite neat. And this proof is one that I would recommend you try it on your own, see where you get stuck, and then try it again. Just keep in mind that we did define up here matrix A to be the matrix of the linear map T, C to be the matrix of the matrix of the dual map of T, and see how this here is just pretty much the same thing we're doing as this over here. So now, slide. I know it's been a lengthy lecture. If you have been watching it all in one sitting, suppose A is an m by n matrix with entries in F. Well, then the row rank of A is the dimension of the span of the rows of A. Similarly with the column rank, this definition should be more clear with an example. So if we have this matrix A here, what's the row rank? And then what's the column rank? Well, to find the row rank, just split it, your rows, and those two vectors we see 4718 and 3529. Those are not multiples of each other, right? So they're independent. So the rank is 2 because those two vectors span a space of dimension 2. Now the columns, instead of splitting the rows, we split the columns. So we have all those four vectors now. And these two, well, we can see that those aren't linear scalar multiples of each other. So the column rank of A is 2. Now, why is it 2? Why isn't it 4? If we have 4 vectors. Well, remember this here, F21. The dimension of that is just the dimension of, the dimension of this is just equal to 2 times 1, which is equal to 2. So it can't be a higher dimension than 2. And we know this is at least dimension 2. Those vectors span at least dimension 2. So we get that A is, the column rank of A is 2. Okay, so moving on, the last two theorems. Suppose V and W are finite dimensional and T is a linear map from V to W. Then the dimension of the range of T equals the column rank of the matrix of the linear map T. So this proof, suppose V1 to Vn is a basis of V and W1 to Wn is a basis of W. Well, the function that takes the vector W, which is in the span of TV1 to TVn to MW, is just an isomorphism. Right? And this is just really seen as how we're defining the matrix, right? If you remember the matrix of T, TVK, right? The sum of the columns, if I remember, of ARKWR. Right, so using this, we can see this, that there's an isomorphism from the span of T1 to Vn to the span of the matrix of TV1 to TVn. That just comes from how we defined the TVK. Therefore, the dimension are equal, right? The dimension of those two are equal because there is an isomorphism. And this here is the column rank of the matrix of T. So we can see that the range of T is simply equal to TV1, the span of all the vectors of TV1 to TVn. Therefore, we have that our theorem holds. And again, you may have to review the section of matrices, but again, it's not too difficult to see once you are comfortable with the definitions of how we're defining TVK, and it shouldn't be too hard to see that isomorphism. But finally, we have that if A is a matrix, an m by n matrix, then the row rank of A equals a column rank of A. So this theorem is a pretty important one. I'm sure you've seen it if you've taken an introductory to linear algebra course, or if you've taken a matrix algebra course, where the rank of a matrix equals a column rank. The row rank equals a column rank of the matrix. And this proof really just comes from a bunch of equalities again, like a bunch of proofs we've been seeing in this section. So the way we're going to go with this, is we're going to define the linear map T of the vectors, the matrices of n by 1 to map to the matrices of m by 1 by T of x equals A of x. What does that tell us? Well, that just tells us that the matrix of T is equal to A, where the matrix of T is computed with respect to the standard bases of Fn1, Fm1. And now we have that the column rank of A is equal to the column rank of the matrix of T. Right? And that equals to the dimension of the range of T, which comes from where? Well, the previous theorem. And that is equal to the dimension of the range of the dual map of T, which again comes from a theorem we just saw not too long ago, that the dimensions are equal. That is equal to the column rank of the matrix of the dual map of T. Now, where do we get that from? Well, again, that's just from the theorem above. You can see And this is equal to the column rank of A transpose, which again we got from theorem. This theorem was from the last slide, right? This and this. Are equal. Therefore, and that's equal to the row rank of A, and that just comes from the definition of transpose, right? The column rank of the A transpose is just the row rank of A, and we get our theorem that our theorem is true. Column rank of A is equal to the row rank of A. So I know this section was quite lengthy. We'll just end up with a definition, which is last thing. So the rank of a matrix A is just the column rank of A, or we can say the row rank of A. Doesn't matter, but that is the rank of a matrix A. And that's our lecture.